Finite-size atmospheric channels, yeah.
Okay, good morning, everyone. First of all, I would like to thank the organizers for the chance to give a talk here at this wonderful QKD-oriented conference. Definitely it will be less complex technically, but I hope still conceptually interesting. I will speak about the proof of principle test of continuous variable QKD in the free space channel, which was done in collaboration between University in Olomouc in Czech Republic and Max Planck Institute in Erlangen in Germany. So I will quickly describe or recapitulate what is the continuous variable QKD, because it's one of the few talks on this subject here at the conference. I will discuss what is the effect of the fading channels on the security of that. We will speak about the possibility to apply post-selection of subchannels to restore the security, and then I will briefly speak about the proof of principle test, describe the further plans, and finish with concluding remarks. So luckily, I don't need to introduce QKD to the audience and the motivation. I would switch to the CV immediately. So basically, it's the attempt to go beyond the single particle statistics, the single photon statistics, and use the quantum multi-photon states of light. And we are considering mainly the coherent state-based protocol, which was suggested in 2002 by Frank Grossans and Philippe Granger. So it's based on the laser source, Gaussian quadrature modulation. So basically, it's the observables which are similar to the position and momentum of a single particle in quantum mechanics, and or equivalent, and the homodyne detection at the remote side, which is fed by the local oscillator. And the idea is that LE generates two Gaussian random variables, displaces a coherent state according to these two. Then Bob measures a quadrature obtaining either of the values. Surely they would be affected by the channel. Then they perform basis reconciliation, error correction, private simplification, similarly to the discrete protocols. And the idea is that the mixture of these coherent states displaced according to the Gaussian distribution would be a thermal state. So in a sense, the state which propagates here through the channel from the point of view of Eve would be a thermal state, while Alice and Bob would be correlated within the coherent state in each of their measurements. And the current achievements of the protocol, I mean, previously it was shown that it can achieve a few kilobits per second at 25 kilometer distance. Then it was improved to 80 kilometers and hundreds of bits per second at this maximum achieved distance by now. And concerning the security, so it was shown that the protocol is secure against collective attacks in the asymptotic regime and in the finite-size regime. Then it was studied against the general attacks. A lot of work was done by Anthony Leverrier in this. So it was shown in the asymptotic and the finite-size regime. Then there was a composable security considered, which is a way to characterize the cryptographic system as a whole, taking QKD as a part. And there was the asymptotic security shown for that, with some hints also how to do it in the finite-size regime. And the advantages of CV, if one may say so, is that we have the large alphabet, we have no empty pulses. So whenever we measure, we get the key bits. I mean, we get the information that contributes to the key. There's no need for decoy states. There's mode selective homodyne detection, so we can effectively filter out the background radiation. And it's relatively simple, so in principle it can be even done on a chip. I know that there's ongoing work in this direction in Albuquerque and in collaboration with Waterloo and with Stanford. And the issues which we still have in CV is that surely it feels the continuous influence from the environment. I mean, when we have a single photon protocol or qubit protocol, whenever the qubit finally gets to the detector, it's most likely is measured correctly. I mean, if environment did not disturb the degree of freedom which was used for encoding. But continuous variables, they feel the environment constantly, continuously. It can be attacked. There can be implementation-based attacks, surely. It can be the local oscillator can be attacked, which is a phase reference for the homodyne detection. It can be solved by monitoring, by self-reference protocols, by classical locking between two remote stations. Then there can be definitely side channels in the trusted devices and other loopholes, which can be overcome by possible measurement device or complete device independent, which was already shown by a few groups. And there was the issue with the post-processing of Gaussian data, but it's mainly solved. So there are already the effective algorithms for that. And concerning the environment which is used as a transmitting media, so it was well studied in the attenuating channels, then the channels with the excess noise or the, for example, detector noise, which is attributed to the channel, so it's attributed to the effect of Eve. And the fluctuating channels were not so much studied before, so this is what is the subject of our research. So basically, we analyze CV QKD in the free space channel, and we perform the proof of principle test of that. So what is the trick about the free space channel from the point of view of QKD is that the transmittance is not stable compared to the fiber link. I mean, where you can fairly assume that transmittance is fixed. So we characterize the fading channel, the atmospheric channel, by a distribution of transmittance values with some probabilities, and it's typically caused by beam wandering in the mid-range channels. So the beam is fluctuating, is traveling around the aperture, and it's not all the time hitting the aperture fully. This can be solved by spatial filtering, possibly, but that would increase loss. So we look at what we can do if our media fluctuates. So first we studied it theoretically, taking security. I mean, we used individual attacks just to show the security bounds. I mean, where the protocol is completely destroyed, where security is not anymore. And then we studied security against collective attacks, so studying the lower bound on the key rate, difference between mutual information between Alice and Bob, and Holivo bound in the reverse reconciliation scenario. I wouldn't go much into details of that. And to study the security of the protocol, we switched to the equivalent entanglement-based representation. So it's actually the purification of Alice's preparation of the coherent state. So we've derived some bounds on the fading variance, so variance of the fluctuation of transmittance, which bounds the security, and it appears to be depending on modulation. So, I mean, since it's a Gaussian protocol and we rely on the extremality of the Gaussian states, it provides us a very elegant mathematical framework of covariance matrices, which we can use to analyze the security. So we study how the fading channel affects the covariance matrix. So for each of the sub-channels, we get the evolution of the covariance matrix, and then the overall channel, which is fluctuating, affects the overall state as the convex sum of the covariance matrices of the individual sub-channels. And then it turns out that effect of the fading channel can be considered as the fixed type channel plus additional noise, which is resulting from the fading. And this additional noise depends on the variance of the state. So the stronger we modulate, the more noise we will have, which is a bit maybe counterintuitive result, because typically, I mean, in the fixed transmittance protocols, it was expected that we can modulate as much as we can and we get the best performance if our post-processing is perfect. So we have this excess noise, which is dependent on the variance or on the modulation depth. And when we look at the security bounds, how much our security is undermined by these fluctuations, then we can derive what are the limits on the variance of the fluctuations, and it turns out that they indeed depend on the modulation variance, which is here, for different mean transmittances. So there is always the optimal modulation which one can apply to the coherent state to get the best performance, and if we increase the modulation further, then it's getting worse. And we suggested the idea of post-selecting the subchannels. So it's not that we post-select the data, I mean each individual bit, but we rather estimate particular occurrences of transmittance values, and we select the particular subchannels which will contribute then to the key. So basically we show security for each particular subchannel, and then we join them together. It can be optimized. I mean, the simplest case would be to select the highest transmitting subchannel, but then the probability would be low. So if one takes into account the overall probability, if one weights the key rate basically by this probability, then this post-selection region should be optimized. And as I mentioned, it should be in addition followed by the channel estimation. So we should know the channel to analyze the information leakage. And then we studied the effect of the real fading channel, which was measured in Erlangen. This is 1.6 kilometer link. I will later show the picture, how it looks like at top, I mean, on the map. It can be well fitted by the Weibull distribution or log normal distribution. I mean, according to the theory which guys in the University of Rostock developed, they are doing quite some work in modeling these atmospheric channels for the quantum communication. And this particular channel can be characterized by particular values of the channel transmittance and channel fluctuations. And we've shown that by applying optimal post-selection, I mean, if this is the post-selection region, basically this is the beginning of our post-selection. As we move from the zero transmittance, as we move further to the perfect transmittance, we can improve the key rate and indeed achieve some optimal performance depending on what was the modulation of our state. So this is the actual distribution of transmittance values, and the gray area is the optimal post-selection region for the given modulation variance. And we also studied how this method of post-selecting subchannels can be affected by the finite-size regime, because definitely we reduce the data ensemble by that. So we performed some numerical simulation, which is also the beauty of continuous variables, because we can actually generate the Gaussian distributions, propagate them through the beam splitters, basically achieve the statistical distribution of an entangled state, then perform conditioning on one of the arms. So based on that, we've shown that our result is quite stable with respect to the finite size effect already for 10 to the power 5 points. So that was the theoretical work, which was published already a few years ago. And then we decided to try this proof of principle test in collaboration with the Max Planck and Erlangen. So they have this mid-range free space link where the beam fluctuation or beam wandering mainly causes the transmittance fluctuation. And the conceptual sketch of the experiment is given here. So we have a laser system. Alice is modulating X and P quadratures, and then there is monitoring on Alice's side to know what was the state that we've prepared. Then it propagates through the free space channel, and then it's measured on the remote side by the double homodyne detection. So there's classical data obtained here by Bob, and there's classical data which Alice puts into the modulation. And for the proof of principle security analysis, we've modeled Eve's attack as an entangling cloner. So basically, we used entangling cloner as the purification of the channel noise now in this case. And so we performed binning of the transmittance and analyzed the security in each particular subchannel. And we found out that there are subchannels in which we observe the positive key rate, while in subchannels we don't, because of some residual fluctuations of transmittance there and also of the intrinsic noise of the apparatus. So we were then, we've ranked the subchannels according to the key rate, and we were basically adding them one by one, expanding our post-selection region, and we achieved some optimal performance. So this is the key rate weighted by the overall success, and this is the number of the subchannels which we were adding to our post-selection range. And we can see that we can gradually improve this key rate, but then as we add more and more and more such channels, we start to degrade it, and basically then it drops below zero. So for the whole transmittance, the security would not be possible. I mean, if we take the whole range, if we don't post-select. But if we optimally post-select, then we can restore the security and optimize it. And what we plan to do next is we plan to realize the squeeze state protocol, or actually it's the ongoing work already. So it will be the Gaussian modulated squeeze state protocol, because we've theoretically shown that if we compare the performance of the Gaussian protocol, this is the graphs that I show, so dependence of maximum variance of fluctuations of transmittance with respect to the modulation depth. So if we take the squeeze state protocol, even with some quite low squeezing, which is 1/1.2, and the modulation then in this regime, in the standard protocol, is given by the anti-squeezing, so the modulation depth is fixed. This is why there is no dependence. These are flat lines. So we can quite improve the performance of the protocol, and even we don't need, in certain conditions, we wouldn't need the to perform post-selection. We would be able to go with the whole transmittance range. So to summarize, we've shown that these transmittance fluctuations, the fading, they affect security of QKD protocols based on the Gaussian states. Then we've shown that states with a higher variance or with a stronger modulation are more sensitive to fading. But if there's additional noise present, then the modulation should be optimized, because there's a trade-off between sensitivity to noise and the the amount of modulation which we put on top of the states. Security can be restored by the use of post selection, or it can be optimized. Alternatively, we can use the squeeze states, which are more robust, which the protocol on the squeeze states is more robust to fading. So it can go even in principle without post selection. And with this, I thank you for the attention.
Thank you, Vladyslav, especially for the good talk and keeping the time excellently. So there is enough time for questions now, please.
I have a question about the experiment performed in London. Why did you use or needed to use double homodyne detection?
Well, we wanted to characterize the channel. We wanted to know it in both X and P, and well, also for the coherent state protocol, I think it's a better choice, yeah, because we are encoding in both observables and we are obtaining information from both.
Okay. Thank you.
Yeah, please, Frederick.
Yes, about your subchannel selection, how much data, I mean, if I understood correctly, you take a run of time during you estimate that eta is constant. How much point you have in each time run, and how much point you have in this global?
I mean, it quite depends on the repetition rate. And surely the faster you fire your states and faster you measure, then more states you can transmit during the stability time of the channel. The overall amount of data points in this case was about 70 million, and after the post-selection, it was few millions remaining. So for the proof of principle, it's sufficient, but for the real implementation, I think we would need longer run and faster repetition rate. And this is the ongoing work which is also being done in Erlangen now.
Yes. Further questions? So I would then ask you also a question. So with this result, you have also run a simulation. Did you estimate at which distance or which attenuation you actually get some reasonable key rate, let's say 200 bits?
It's hard to talk about distance in this regime,
no,
right?
Attenuation, I mean.
Yeah. Well, it was a few dB scale, yeah, because we were interested in mid-range channels rather. So I don't foresee really long distance application in the free space link, because definitely you need line of sight. Yeah, so you cannot go to hundreds of kilometers with that. So yeah, I mean, the transmittance was about 10%, roughly.
Okay, thank you. So further questions? So if no, we can close this section, and I think the organizers maybe will announce something about the forthcoming excursion. Yeah. Thank you very much. Let's thank the speakers. Thanks, Vladyslav.